Thank you. Thank you very much, Nicola, for this nice introduction. It's a pleasure to be here. I really want to thank the organizers for doing such a great job. I know how hard it is to organize a big conference in the middle of a pandemic, so thanks a lot for that. So Nicola was hinting, that 10 years ago, we were both starting a PhD, being office mates and stuff. So I think my story with Durham goes further back than that, because I think a lot of you already know, but my first experience doing graph theory was actually in Durham when I was just about 19 years old. I came to do a research internship with Matthew Johnson and Daniel Paulusma. Everything started from there, looking at corings, recorings and stuff. And I used to do an annual pilgrimage to Durham every year in July, actually, just now. But of course, COVID has deprived me from that, among other things. So yes, today I want to tell you about something which comes back a bit to the genesis of things, as Nicola said, decomposing the edges of the graph. So mostly it's just an excuse to tell you about two of my favorite conjectures in regarding partitioning the edges of a graph into some special structures. So throughout the talk, feel absolutely free to interrupt me if anything I say is unclear. Everything, like if you want to clarify anything or I said anything ambiguous or I spoke too fast, it's perfectly fine to just interrupt and ask for precisions. So when you think about decomposing the edges of a graph, the most simple, most common way of doing it is through edge coring. So you have a graph, it's simple, it's not oriented or anything, it looks basically like this. I mean, maybe it's more complicated, but still something like this. And you're trying to color the edges of it. So what does it mean? It means that around every vertex, you want to make sure that you don't see twice the same color. So for any vertex, the edges incident to it all have distinct colors. And of course, I mean, if you don't care about the number of colors you need, it's not very interesting. You could just use different color for every edge. We don't really care about that. What we want to do is minimize the number of different colors you use in the graph. So that's something which is called a chromatic index, which we call K prime. And throughout this talk, I'm going to drop the parameter. I mean, it's K prime of G, but I don't think it's going to confuse anyone if I just don't ever say of G throughout this talk. So you're trying to minimize the number of colors you need to color the edges of a graph in this way. So what's a really trivial lower bound you can think of? So whenever you have a vertex of high degree, you can see that you need a distinct color for all of the incident edges, right? So that's a trivial lower bound. Whenever you have vertex of high degree, you need that many colors to color the graph. So a bit more formally, if you look at the maximum degree of graph, which we usually denote by delta, which is the max number of neighbors a vertex can have, that's a trivial lower bound on the number of colors you're going to have to involve to color your graph. So that's the very naive, easy lower bound. What can we say about the upper bound? So if you try to color the edges in a naive way and just like pick an ordering of the edges and just like step by step look at a new edge and try to assign it the smallest color, which was not used so far, you can imagine that there would be cases where you need as many as twice delta colors, because I mean, maybe when you look at an edge, it has actually both endpoints being of degree delta, and maybe all the edges around are already colored and they all use distinct colors. So it's roughly twice delta as a trivial upper bound. So the nice thing about edge coring, which is very different from vertex coring for those of you who are familiar with it, is that you can do a lot better than the greedy upper bound. And what we can do is actually one of the first and best known results about edge coring is actually color any graph with just at most one more color than the trivial lower bound. So it's really quite a striking result. It really says you have this really stupid lower bound, which is obvious, and well, there are some graphs which you can color with that many, but worst case scenario, you just need one more color than that. It's quite a surprising result if you think about it. And the thing which makes that result all the more interesting to me is that we have many different proofs of it, but there's one tool which is in every single one of them, which is the notion of compare change. So let me say a few words about compare change before I tell you why it's useful to prove using this theorem. So again, you have a graph, you have an edge scoring of it, and how do you do a compare change? So you pick your two favorite colors. Let's say for now your favorite colors are blue and red. You look at the connected component of the graph induced by these two colors. So if you look at the graph induced by these two colors, it's just, you know, this path on four edges. It's connected. So, well, there's only one connected component. And what you can do is swap the colors there. So the new coring you get is this one. So really red become blue and blue become red. And here you could be a bit unhappy and say, sure, but it's not really a different coring, right? Because edges which had different colors still have different colors. Edges which had same colors will still have same colors. So it's really just the same coring. I just, you know, relabeled it. It doesn't seem like it's really a different coring. But okay, my choice of blue and red was maybe bad at the beginning. Let's pick a more interesting choice of colors. Let's say now our favorite colors are red and green. So now when you look at the graph induced by red and green in the graph, you have this edge here. It's just alone. I mean, it doesn't have any green neighbor, but it's still like a green and red component. And you have this path on two vertices here. So you need to pick one component. So you can pick the bottom one, say, and you get a new coring. And now here you can say, you can really see it's a different one. I mean, it's still a proper coring. I mean, you can check that whenever you do this kind of compare change, you always obtain like something which is still net coring, satisfying the same properties as before. But you kind of play a bit with things in a local way. I mean, semi-local way. So yes, you can do this, and then you get a different coring. And you can do something which is perhaps even more interesting. You can pick at the beginning the edge which is alone. And here now, swapping the colors means, you know, that you just have this single edge, and its color goes from red to green. It doesn't have any neighbor being called red and green, so it doesn't impact anything else. So what this means is that if you didn't have any other edge called red in the graph, then you would have gotten rid entirely of the green color, of the red color. So that's one way you can modify the corings. So really you start from any coring you like, and you can think about what kind of thing you can obtain, how far you can go, what kind of property you can obtain through these kind of compare changes. So just to make sure we all agree on what a compare change is, one nice observation, I mean, it's not a very deep observation, but it's still like good just to fix things in your mind, is that whenever you look at the graph induced by two colors, I mean, the subgraph induced in your graph by two given colors, every component is just either a path, I mean, maybe just one edge, but that's a special case of path, or a cycle, I mean, even cycle even. So I mean, the structure is quite restrained. So let's see how to use it. So essentially, to prove Ising's theorem, what you're going to say is, well, I'm going to start from an arbitrary edge coring, which is going to use, I mean, if it uses at most delta plus one colors, then I'm happy. I know there is a delta plus one coring of my graph because that's what I started with. But now let's say we start from a coring which uses more than delta plus one colors. So what we're going to do is try to get rid of those extra colors. So say we have color delta plus two somewhere in the graph. So say it's here, you have at least one edge UV being called delta plus two, and maybe like lots of others. But you're going to try to get rid of them. All of them, you're going to try to color those edges instead with a color which is appropriate. So by appropriate, I mean like in the range of between 1 and delta plus 1, without creating new edges being colored delta plus 1, delta plus 2. So I'm just going to try to get rid of this. And the key thing, I mean, it's not a very deep observation, but because you have at least delta plus 2 colors involved in the graph, what this means is even if you restrict yourself to the range of appropriate colors, so again, between 1 and delta plus 1, you know that's at least one color, actually more, but we don't care. There's at least one color around each vertex, which does not appear around it. So for vertex u, for example, you could say color 3 is missing, meaning there is no edge incident to u, which is color 3. And if by miracle, it's the same for v, then you're very happy because you're going to do a compare change 3 delta plus 2 on this edge. And because there is no incident edge being color 3, you're going to, you know, decrease the number of edges being colored delta plus 2 by 1. And, you know, you can then keep going. So really, the general approach is you have an edge coring which is bad, and you're going to fix it step by step until you have no more edge being outside the appropriate range of colors between 1 and delta plus 1. So that was a really good case scenario. There's no real reason why the same color would be missing on both sides. So let's assume it's not the case. So you have a different color missing on the vertex V. But then what you can say is, well, so there's some other edge incident to V, which is called a 3, right? Otherwise 3 would be missing. And here again, you can do a slight case analysis. You can say, okay, if by any luck I am actually missing the same color as before, I mean as vertex V, then I can do a 3-4 combit swap on that edge, and now I'm back to the previous case, right? So this does not happen. So you have a new color, and you can keep going, keep going, keep going. You always, you have to miss a color which is not the same as your endpoint, and so on and so on. But this cannot go on forever. So how does it stop? How does the process stop? So it stops if you see some color which you saw before. So here's some case of it. So you see again missing color 3, which you saw before. Well, actually at the very beginning, it was the missing color at the vertex U. So the key observation, and I cannot emphasize enough how important this lemma is whenever you try to do edge scoring in such graphs, is that a path has at most 2 endpoints. So when you look at a component 3, 4, you know that maybe it has one endpoint being V, maybe one endpoint being U, but at any rate, it does not have as endpoints simultaneously U, V, and X. It's it's simple, but it's really important. And so what you're going to say is, well, I'm not going to give you the whole case analysis, I promise, but essentially you do a 3, 4 combination on V, and you can impact maybe X, maybe U, but not both. And what you can prove is that regardless of which one you impact, you're back to one of the earlier easy cases. So you're always happy. So this is essentially the proof of Ising's theorem. I mean, hiding a few details in the carpet, but I'm sure you can all go back home and retrieve the details from what I told you right now. So there's something called a Ising fan. So it's really like you have a color you want to get rid of, and you look around and like kind of try to shift it, and then when you can't, that there's some other way to move color around using campaign changes, which allows you to do what you wanted to do. So that's the argument. And what you can see is it gives you a bit of a stronger statement than what I usually claimed. Ising's theorem is there exists some delta plus 1 edge scoring of my graph, whichever graph that is. It's actually what we proved here. I mean, what we sort of proved. I mean, I'm not going to give any formal proof whatsoever throughout this talk. I just want to give you flavors of what's going on. So what we really proved is that no matter which scoring you start with, I mean, which proper edge scoring. So no matter which edge scoring I start from, I can, through a series of compit changes, get down to a delta plus 1 edge scoring. That's what the proof is really about. So you don't really control which delta plus 1 scoring you end up with, but there is one. So in particular, if you start with the delta plus 1 scoring, you have no idea how to go to a different one. I mean, there are some cases where you cannot go to an arbitrary other delta plus 1 scorings. But anyway, that's kind of off the topic. So the point is quite a bit stronger. And just a year later, Ising had a really nice conjecture. So I told you at the beginning of the talk, this talk is a kind of a pretext to tell you about 2 of my favorite conjectures around edge decomposition and stuff. This is one of them. So his conjecture is that instead of just saying from any proper edge scoring, you can get down to a delta plus 1 edge scoring. So you can get down to an edge scoring using at most delta plus 1 colors. What he claims is that it should be the case that you can always get down to an optimal one. So of course, I mean, if your graph needs delta plus 1 colors to be properly edge colored, then, well, that's it. You obtain delta plus 1 edge scoring and you're never going to get anything better. But his conjecture is that if, in fact, your graph does not need delta plus 1 colors, but it needs a delta edge scoring, you should be able to find one through a series of compit changes. So then it seems like a very natural conjecture. So just to give the intuition of kind of why it's so different from Wissing's proof, like kind of why we don't expect exactly the same proof. I mean, a proof is similar flavor to work for the stronger setting where you just try to go to an optimal edge scoring. So you just need to think about the algorithmic point of view. So from the Wissing's proof, I mean, the proof I sketched to you just a minute ago, what you can derive is that there's an easy way, a fast way to obtain a delta plus 1 edge scoring of any graph. I mean, just algorithmically, like you can, I sketched to you how to obtain a 2 delta greedy algorithm, just picking arbitrary ordering, so you can compute a 2 delta scoring easily. And then, using this Wissing fans and stuff, you can step by step decrease number of colors until you get to a delta plus 1 edge scoring. And that's actually reasonably fast. So you can do it in time, number of vertices times number of edges of your graph, really fast. That's just, because of the kind of tools which are used in the proofs, just like, step by step getting rid of a color in your scoring. And in contrast, if you think about the stronger version where you should be able to find an optimal one, we know it's actually NP hard to even decide whether your graph emits delta edge scoring or needs delta plus 1 colors to be colored. So we know, we can't hope for such a basic proof as the one there is for Wissing's. But I think it's a very nice miniature. And just to say something about partial results, like, well, what do we know so far? So the results, are not impressive in themselves, but it's just to highlight how hard this miniature is. So there were 2 papers concerning what happens for graphs with small maximum degree. And it's really non-trivial. Like you have a lot of cases and analysis to handle, but you can prove that for graphs with max degree at most 4, the conjecture holds. It's even a bit stronger. It says that if you start from a net scoring, well, either it already has the optimal number of colors, and then essentially there's nothing much more you can do. I mean, there are examples saying that you can't hope to get to your favorite other optimal edge scoring. But as soon as you have one more color available, then you can choose which optimal edge scoring to go to. So not only you can go to one, but you can choose. That's an interesting stronger statement. I mean, it's the restriction of delta at most 4 seems a bit much, but you have to imagine that just to handle the case delta being 4, you have essentially 10 pages of quite intricate case analysis and stuff. So you have to. It's a hard conjecture. And what we proved recently with Oscar Defrin, Terka Klemoshova, Aurélie Lagoutte, and Jonathan Arboni is that for triangle graphs with no assumption on the maximum degree, everything works out. So same thing. Either you start from your favorite edge scoring, either it's already optimal and there's not much we can say, or it's not optimal, so it uses at least one more color, and then you can even choose which optimal edge scoring to go to. And surprisingly, the proof is quite short, meaning it's really just about looking very closely at those Wissing fans, thinking about what kind of structure they force in your graph, and proving essentially that all bad scenarios are tied with triangles. That's roughly the proof. I mean, there are some more ADs than that, but that's essentially just tweaking this notion of Wissing fans and looking straight at them to see what they say about the graph. So it's really not that hard. Like it's basically 4 pages, but it's interesting how bad triangles are. And just to share a bit of my frustration here. So this conjecture, which I think is really nice, natural, and should be true. And it's kind of hard to argue properly that it works for cliques. You have a clique, you know exactly what it looks like. You have all those edges and stuff. It's not trivial how to properly argue that all the scorings are equivalent if you have just one extra color. I mean, you can't apply induction, obviously, because you leave the realm of cliques. So yeah, if you think that this conjecture shouldn't be that hard, please think of cliques and find a good argument to handle them. I mean, it's quite clear, it does work, but it's not clear what's the general argument for them, like for dense graphs in general. So yeah, I mean, we tried very hard to extend this. So we think we can prove it for diamond free graphs, but then the proof gets extended by 20 extra really ugly pages of proof. So we felt, it's best to stick to triangle-free and, have a reasonably nice and short proof. So anyway, so that's kind of the setting for the conjecture. One thing, I mean, if you know me a bit, you think that the next obvious question I'll ask is, what happens for planar graphs? It's kind of frustrating, right? I mean, you have these things which work for kind of sparse graphs, like small max degree or triangle-free. So what about planar graphs? I mean, that's usually a good scenario for a sparse class. It's usually some place where things behave the way you would like for them to behave. So unfortunately, I can't tell you yet what's the full picture there. We have partial answers, but not the full thing. What I will tell you about, I mean, I said this talk was a pretext for me to tell you about two of my favorite conjectures. I lied a little bit because it's also a pretext to tell you about some proof techniques I like. So for planar graphs, one technique which is super helpful, it's not always very pretty, but it's usually pretty helpful. And I promise I'm not going to go into the ugly details. I'm just going to tell you again the flavor of why it's nice and why it helps for this kind of thing. So it's about discharging. I am sure Nicolas saw this coming from miles away, but still. So discharging, something which was introduced many years ago as an attempt to prove the Foucault theorem. I mean, it didn't work at the time, but it's still a crucial tool in proving the Foucault theorem. So it is heavy machinery. It does help with getting stuff proved. So what is it about? So essentially, it's just double counting. So how do you do it? So, I mean, I'm going to start with examples which are not in graph theory, and then, slowly go down to things in graph theory, but just like trying to tell you how those things work. So the first example of discharging, I'm sure you've all seen it before, but maybe you didn't think of it as discharging. If you're trying to count the sum of integers between 1 and n, so one thing you can do is assign to each element, each integer, its own value as a weight. And then you're going to do a double counting, you're just going to reassign, shuffle a bit the weights around in a way which makes them easier to count in the end. So I'm sure you've all seen this before, but essentially like the lowest gives all its weight to the highest and so on and so on. And so that's the discharging rule. The kth lowest integer gives its weight to the kth highest integer. And so you apply the discharging and then you see what's left. So you have exactly the same sum of weights as before, but as you can see, it's now easier to observe. So you have, the lower half, which has all new weight 0, and the upper half, which has all the same weight of being, n plus 1, if n is the number of integers you're looking at. And then it's trivial, what the formula should be for this. So let's apply this reasoning to a different setting, to a slightly more involved setting. So we're talking about planar graphs. I'm sure, if you think about planar graphs, one of the first and useful things you can know about planar graphs is Euler's formula. So, I mean, I said formula, but I didn't give the sum yet. So you're trying to compute, you have a planar graph, and you're trying to compute number of vertices minus number of edges plus number of faces. So you have your favorite planar graph. Let's say it's this one. I mean, you'll see it's kind of a generic example. If you understand this one, then you understand all the planar graphs. You just make sure to draw it in such a way that no edge is perfectly horizontal. That's always easy because, I mean, if that's perfectly horizontal, you can just like tilt the graph a tiny bit, and then, nothing is perfectly horizontal. So you're just going, I mean, I said discharging was about, assigning weights and then shuffling them so that they're easier to look at, I mean, easier to compute. So you want to compute this in a planar graph. So number of vertices, that's just sum of 1 for every vertex. And minus number of edges, that's sum of minus 1 for every edge. And plus number of faces, that's, well, sum of 1 for every face. So you should just make sure not to forget the external face, because that's easy to forget, but still it's there. And now we're going to define one single, very simple discharging rule, which is that every vertex and every edge gives all its weight to the face that's to its right. I mean, I realize now I'm doing the animation in the wrong direction because I'm looking at the screen the wrong way. But anyway, I hope it doesn't confuse you too much. So yeah, every vertex and every edge gives all its weight to the face to the right. So let's look what happens once you've done that. So once you've done that, so yeah, you have this discharging rule. And after you've done this, well, clearly every vertex and every edge has a new weight of 0. Because I mean, they gave all their weight away. They didn't receive anything new. So essentially, if you're just trying to compute the value of this sum, so number of vertices minus number of edges plus number of faces, you can forget about them entirely. So let's look now at faces. Let's first look at an internal face. So it started with a weight of 1. Like, let's see what this one receives. It receives like -1 plus 1 minus 1 plus 1 minus 1. Essentially, the idea is it's going to receive weight from a series of edges, vertices, such a way that you never have 2 consecutive vertices, you never have 2 consecutive edges. It has to start with an edge and with an edge. So it receives, you know, -1 plus 1 and so on, -1. So it receives -1. So its final weight is 0. So if you want to compute this in a planar graph, you just have, you know, to do this weight assignment we did, do the discharging rule, and then you just need to look at the final weight of the external face. That's all you need to look at if you want to compute this sum. And what happens for the external face? Well, essentially the same as internal face, except that maybe now, you know, the starting point is a vertex and the end point is a vertex, but then it's still, you know, going to be an alternation of vertices, edges, and so on. So it started with 1, it received a total of 1. Well, I mean, 1 per connected component, but in this case, you get a final weight of 2. So that's, I mean, it's not really a very formal proof. I mean, you can make it formal, but it doesn't have any point compared to the usual induction argument. So the point here is just to give a visual proof of Euler's formula, and again, tell you roughly what discharging is about. So you have weights, you don't know how to compute them, you shuffle them around and try to see what they tell you. So more generally, how do you use them for coring problems? So the way the proof goes, typically, I mean, I'm not saying all proofs are that way, but this is a typical outline for a coring proof. I mean, a proof of a coring theorem using discharging, especially for planar graphs. I mean, it works in other settings, but essentially mostly sparse settings. I mean, you can always, you know, take that mindset and put it in other places, but that's the most common one, say. So what you want to prove is that every planar graph contains some configuration. I mean, I should mention every non-empty planar graph, because of course, if your vertex contains neither vertex nor edge, then it doesn't contain anything, but it's not particularly interesting. So every non-empty planar graph contains some configuration in some list. So something we call unavoidable configuration. So for example, I mean, just to make sure we're all on the same page, I could make a list of 1 by saying every non-empty planar graph contains a vertex of degree at most 5. That could be one configuration, a vertex of degree at most 5. And I know for sure every planar graph which has at least one vertex has a vertex of degree at most 5. But it's just an example, like it can be a lot more complicated than just this. And then you're going to say, well, for the problem I'm concerned about, actually, whenever I mean, if I look at a minimal context example, or I'm just, you know, trying to find an algorithm or something, if I see one of those configurations, then I'm happy. There are many ways to, you know, argue you're happy, but somehow you can say, if I see this configuration, then I can get down to an instance of my program which is on a smaller graph, and then, you know, either I apply induction or, you know, I reach a contradiction with minimality of my example or stuff like that. But anyway, the message is, if I see one of those configurations, then I'm happy. So it's reducible configurations. And then, you know, combining the two, I mean, you have to make sure, you know, you contain the same list of configurations for unavoidable and reducible. But then you get, you know, that you put the 2 of them together and you get that every planar graph with the right hypothesis satisfies the property you wanted. So I gave an example, which is, you know, that every planar graph with max degree at least 7 is actually delta edge corable, meaning you never need delta plus 1 colors. So that's a real proof which really relies on discharging and really contains a list of unavoidable configurations which are all reducible for the problem of being delta H correlable, assuming delta is 7. And so you can say, okay, that's good, but where is discharging here? So discharging is not in the reduction, because reduction usually you just do an ad hoc thing saying if I delete this edge or replace this with that, then I'm going to be fine. The discharging appears in the first part when you say every planar graphs contain some configuration among that list. So what does it look like? So you go back to Euler's formula. So Euler's formula, I mean, we don't really care about the number of components or anything. We just want to say number of edges minus number of vertices minus number of faces is negative, strictly negative. Actually, you can rewrite this a little bit when you have to multiply by 6, whatever. But you can rewrite this a little bit by saying that the sum of our vertex of its degree minus 6 plus the sum for every face of twice its degree. So the degree of a face is just the number of edges in the boundary. So sum of for every face of twice its degree minus 6 is, I mean, this sum for every vertex and for every face is strictly negative. But you're in a plane, I mean, you're going to do proof by contradiction and say, assume you have a planar graph non-empty, which contains none of the configurations I wanted. You want to say that you can't simultaneously satisfy Euler's formula and contain none of those configurations. So what you're going to do is just, see this as weights that you assign to every vertex and to every face. And then you're going to shuffle them around following some appropriate discharging rules. And then say that at the end, everyone has non-negative weight. Just, using the fact that everyone has, I mean, that none of the configurations appear in the graph. So just to give you an example, if you want to prove just very simply that every planar graph contains a vertex of degree at most 5, all you have to say is, well, assume that's not true, then every vertex is degree at least 6. But then, then by definition, the weight of every vertex is non-negative, because degree minus 6 is always going to be at least 0 if you don't have any one of degree at most 5. And twice the degree of the face minus 6 is also always going to be non-negative, because the boundary of a face is always at least, well, the worst case is it's a triangle, and you can check that's also non-negative. So that's immediately a proof that every planar graph contains, every non-empty planar graph contains a vertex of degree at most 5. And of course, you can do way more involved. You can obtain way more involved results for planar graphs using this. So just to give you a flavor of what discharging proof looks like and why it can be useful. And I mean, so this is the high-level view, and then when you get down, unfortunately, you often get to quite a few case analyses and stuff. It's not always the case. Sometimes you kind of see a right way to do it in a way which is convincing and which allows you to not do too many case analysis. But for example, for the four-color theorem, that's the proof behind, and you have over 600 unavoidable configurations, and you have over 600 discharging rules to prove that they are indeed unavoidable. And then you need to prove that each of those over 600 configurations are reducible for four-coloring of planar graphs. So you can see why exactly this proof is computer assisted. Anyway, so that's all I wanted to say about discharging. If you have questions about discharging, feel free to ask them now, or when you can also ask them at the end of the talk. I'm sure I will remember about discharging by the end of the talk, but if anything is unclear, I think that would be a good time. So at the beginning, I told you that this talk was pretext again to tell you about two of my favorite conjectures around this topic. I told you the first one was this Weising's conjecture about can you always get down to an optimal edge scoring through a series of compute changes? What's the second one? So the second one has to do with path decompositions. So now we don't do corangs anymore. We're not trying to, have have only local constraints and like bound and total number of colors, which is used having, the property that every color can be used arbitrary many times as long as it's never used twice around the same vertex. Now I have a slightly different point of view. I want to decompose the edges into paths, but now I want to make sure that, well, every color, I mean, if I want to use the color setting, every color is a path. So it's only used once. I mean, it's only one path. And trying to minimize the total number of paths in your graph. So if I look at a triangle, how can I decompose this in path? So actually, you only have 4 options. I mean, up to permutation. So essentially, there are 3 options where you have 2 paths. So essentially, you just each time you take your favorite edge as a separate path, and put the rest as a second path. And you have one solution where you just take a distinct path to each. And just to make sure we're all on the same page about path decomposition, here's the formal definition. So you really want to make sure that every edge is in a path and it's in exactly one path, meaning you cannot use the same edge twice for 2 different paths. So for a triangle, I mean, for K3, click on 3 vertices of triangle. The optimum number of paths is 2, because I mean, here you have 3 ways to partition this into 2 paths. And well, you can see one path is not enough because, well, a triangle is not a path, so you can't just have one color. So what can we say about this? So just one easy observation is that whenever you have a path decomposition of your graph, every vertex of odd degree has to be the endpoint of some path, right? Because I mean, there's no way all paths just go through, since every edge is used by exactly one vertex, one path. You know that, well, whenever you have an odd number, then one of them has to end there. Maybe more than one, but at least one. So lower bound in general, I mean, worst case scenario, all of your vertices have odd degree, and then you can't do better than half number of vertices. So is this always the right answer? Meaning, is it true that whenever you have a graph on n vertices, you can always decompose the edges into at most half n number of paths? So normally, if we were in person, I would see if any of you wants to answer. I can't see right now, so I'm just going to go along and give the answer directly. So, we had the example of a triangle which has 3 vertices and needs 2 paths. Well, if you take a large collection of disjoint triangles, then, well, clearly half n is not the right answer, because roughly for every 3 vertices, you need 2 paths. So, well, that's 2/3 of n, not half. But it's a bit of a bad reason. I mean, it's just most of my talks start with, well, throughout this talk, all graphs are going to be connected, just because in coring usually you don't care about connected components. You can just focus on one, and if it works in every connected component, it's going to work for the total. So here it's not quite true anymore, but still, like, we can ask the same question for connected graphs. And for connected graphs, now it's reasonable. So this is a conjecture by Galay from 1966, saying, whenever I have a connected graph, I should be able to decompose its edges into at most half number vertices path. And it's kind of funny because the intuition behind it is quite simple. Like, either you have a graph which is sparse, and then indeed, like, you don't need many paths per vertex to cover everything, or your graph, has many edges, but then intuitively you can do lots of very long paths and still, cover everything. That's that's a very high-level intuition, and well, we're still far away from proving this conjecture as a whole. But one thing which I find funny is here, when you try to prove this conjecture, or I mean this conjecture in some special cases, it's really annoying to have this ceiling. Because what this means is that if somehow, like when you try to reduce stuff in your graph, if you disconnect your graph, if you have 2 or more connected components, then for each of them, maybe you have an extra plus a half. And so having this connected graph and having this ceiling of half n, there is really hard to work with, because you have to make sure nothing you do disconnects the graph, which is sometimes really annoying. So that's a stronger conjecture. which is that it's always at most a half of number of vertices, no ceiling involved, unless you have too many edges. So what does too many edges mean? I mean, that seems like a cheap way out, saying, oh yeah, no, this graph is not good for me. But too many edges, the proper definition is quite natural. So if you have a decomposition into at most n over 2 path, because each path has at most n-1, at most n-1 edges, then the total number of edges you can have is at most n½ times n-1. And there are some cases, particularly like odd cliques, where you have more edges than that. And that's precisely the examples where we know you need the ceiling. But essentially, we believe, when I say we, it means like a subset of people working on this conjecture, that these are the only obstructions. So then that's really good news. It's something which is much easier to work with. Assuming it's true. Because essentially it means that you can disconnect your graph unless like one of the components you create is one of those bad cases. And those bad cases are easy to understand. It's essentially just an odd clique minus some few edges, roughly. So yeah, so it means there is hope. It means it's easier to play with things and create components, but make sure that when you have one of the bad ones, then you know exactly what it looks like. When you have a finite list, well, it's not quite finite, but small list of what could happen, and you can work with that instead, essentially. So let me give you some lists, say some idea of what kind of stuff we can say about it. So there's this really, really nice recent result by Girard, Granet, Kuhn, and Ostus from this year. It was published this year, but I think it dated from a bit before, saying that, okay, so this conjecture, we still don't know if it's true or not, but at least if your graph has linear minimum degree, meaning there is some constant such that your graph has minimum degree at least that constant times n, and n is large enough compared to the constant and everything, then there's almost a good path decomposition, meaning it's asymptotically true. So the kind of tool used behind that is a kind of really powerful tool. But here I'm interested more in the other end of stuff. Like you could say it's more the pedestrian approach, but just trying to confirm the conjecture fully for some sparse graph classes. So it's really the other, the entirely different approach to it. So first recent result, like trying to prove something general about it. It's not so recent anymore, it was 5 years ago now. Saying again, if your graph actually has small max degree, you can make things work out. So proof is not super hard, but it was one of the first few results, which deal with a kind of generic graph class. There are lots of results, very interesting ones, but about graph classes with kind of unusual restrictions on the structure. For example, saying that the vertices of even degree, if the vertices of if the vertices of even degree induce a forest, then the conjecture holds. This kind of stuff, which is very strong results and hard to prove, but it's satisfying to have at least some somewhat generic graph class where it's confirmed, even if it's not super exciting graph class like graphs with max degree at most 5. And actually max degree 6 is surprisingly harder. I really thought at first that someone would show up a year or two later saying actually you can go quite a bit beyond that, and it really seems that there's a harsh jump from 5 to 6. Anyway, so another very nice result about this was saying that if you look at triangle-free planar graphs, see, we're going back to planar graphs, I told you this would come in handy. If you look at triangle-free planar graphs, then the conjecture holds. And here you can see one tiny detail, which is that there is no floor here, no ceiling here. So actually what they did is prove the stronger version where we say, you actually get half of n unless you have too many edges. And the thing is, in a triangle-free planar graph, you can never have too many edges. So that's essentially why they don't have any special case. They say, whenever I have a triangle-free planar graph, everything works out. And what we proved very recently with my patient, Alexandre Blanchet, and a colleague, Nicolas Bonichon, is that for planar graphs, it also works. And here, you know, because some planar graphs can actually have too many edges, we do have two exceptions. So we also prove, you know, half of n without seeding, but in exchange for that, we need to forbid, I mean, not forbid, but we need to handle two special cases, which are, well, the graph just being a triangle, because, well, if you're a triangle, then clearly you need two paths, and you only have, I mean, you should only be allowed 3 halves, which is not enough. And same goes for K5 minus an edge. So K5 also has too many edges, but it's not planar, so we don't need to worry about it. So these two graphs are the only planar graphs with too many edges. So yeah, I mean, there are lots of results I'm not mentioning, for example, having a better upper bound in general, like saying you can always do 2/3 of n, or, you know, a bit beyond, a bit below that, or, you know, trying to measure the contribution of odd degree vertices compared to even degree vertices, and so on and so on. So I'm not discussing any of this. And also, as I hinted at, there are lots of results about graph classes where even degree vertices have a special structure, or odd degree vertices have a special structure. I'm actually mentioning this, but still, you can see the picture here is that here again, we are very far away from having the whole conjecture. It's kind of frustrating. There are some, yeah, you'd hope, you know, by now we would understand things a bit better. I mean, we do make progress, but the progress is quite frustratingly slow in that respect. So I see I'm slightly running out of time. So I'm just going to give you, again, a flavor of the proof behind this connected planar graph case, and then let you have some coffee. Okay, here's a tiny flavor. I mean, it's not going to give you much, but just, you know, tell you a bit of what's going on. So if you find your degree 2 vertex in your graph, so I mean, you're still in the setting where you're trying to reduce some equation, like see some stuff in your graph, such that if you see it, then you're happy you can get down to a smaller graph. So if you see a vertex of degree 2, which is not in a triangle, meaning its two neighbors are not adjacent, well, it's kind of obvious what you're going to do. You're just going to replace this vertex with one edge, which is fine. I mean, the graph is still simple. I mean, I didn't mention it, but obviously Gauss nature is false if you allow multigraphs, because then, you know, you can have two vertices and like tons of edges between them, and there's no way you can cover this with just one path. So yeah, we really have to look at simple graphs. So here, what do you do? Well, you know, you reduce and you say it's smaller, so I can assume I have a good path composition. So in particular, this edge is in one path. So then I can like obtain a solution of my initial graph. And I mean, keeping everything else the same. Okay, so that was maybe a bit, you know, not enough to give you an idea of what's going on in the proof. Here's a slightly more involved example. I mean, it's just an arbitrary example I chose, but essentially everything is somewhat like that, just a bit more complicated. So if you see a triangle with vertex of degree 2 and one vertex of degree 4, I mean, I'm sure you see this every day. You can reduce it by like deleting those two vertices in the middle and kind of contracting, I mean, essentially contracting the edge UW. So, you know, it's still planar and everything. And you have this new graph and it's smaller, and you deleted two vertices. So now, you know, from a solution of the reduced graph, you can obtain a solution of the bigger graph, and you're allowed to create one new path, which is kind of good news. So here, what could happen? I mean, you know, you have a solution of this because it's smaller. What could happen is you have just one path going through like this, but that's in the second case where you have distinct paths going through. And because you don't know what happens inside of W and stuff, then, you know, so here it's not too worrying, but on the bottom one, like, you know, P could really go through from X1 to W and on to other stuff, and same for Q. And in each case, so in the first case, you're kind of happy because you can just split the path in two, and it's enough to cover. And splitting is fine because, I mean, you had one path with two paths. That's a legal move. And the second one, you're even happier because you don't need to do anything really. You can just like extend, and like you were allowed to create a new path, but you didn't have to. So just this with, well, a lot of similar configurations is enough to tell you that you can assume there's at most one vertex of degree at most 4 ever in your graph. As soon as you have two, you can do similar things and like get rid of both of them, like reduce what you see. So you can assume now that you have a planar graph, it's connected, and it has at most one vertex of degree at most 4. So it's not enough to say it doesn't exist, but you're getting closer. And the extra thing you need is that I mean, we use some old theorem of U. I mean, it's from 1998, and a lot of hard work. By hard work, I mean like 50 pages. You can prove that whenever in your plane graph, you find 4 vertices of degree at most 5, either you can kind of like navigate through them using just 2 paths and like delete the 4 of them at once and be fine. Lots of elbow grease. Or, you have this 4 vertices of degree at most 5, but they are kind of separated from each other, meaning there's a cutoff at most 3 vertices separating them or something like that. And what you can prove using the bit of discharging is that you can't have that. You can't have a planar graph where you have at most 1 vertex of degree at most 4, and whenever you find vertex of degree 5, they are not tied together in some nice 4-connected component or something. So that's the general idea. And just to conclude, so these were 2 of my favorite conjectures in this topic, like as decomposition in general. I hope I convinced you that, well, they are kind of nice, and well, I don't really want to convince you that they're hard, because I'm hoping someone will solve them, or at least make some major progress toward them. But yeah, at least I hope I showed you what's hard about them, say. And yeah, I hope now you see a bit of how this kind of proof goes through. I mean, this discharging and visiting spans if you never saw them. So that's it. Thanks a lot.
Thanks a lot, Marthe. Maybe we can unmute ourselves to thanks Marthe.